In this video, we're going to continue our discussion on the basics of differential equations, and we're going to talk a little bit now about general and particular solutions. And this stems from the fact that solutions to differential equations are not unique, right? So if we're going to verify that they're both solutions, we need to make sure that, remember, we need to plug in the derivative of y into the differential equation. So in this differential equation, you only see the first derivative on the left hand side. So that means if we take the derivative of y equals x squared and y equals x squared plus 4, they should equal the right hand side, the 2x, and then we'll know that these are solutions, right? And in fact, when we do the derivative of x squared, we know that that's 2x. And the derivative of x squared plus 4 is also 2x, because remember, the derivative of 4 is just 0. So they are both solutions. Right, so this confirms that the solution to a differential equation is not unique. And in fact, right, we could find an infinite amount of solutions to this differential equation here, right? So in fact, right, any solution of the form y equals x squared plus c is a solution to the differential equation y prime equals 2x, right? And that's because we know that for y equals x squared plus c, y prime equals, right, the derivative of this is y prime equals 2x regardless of the value of c, right? So that means that we could have had like, for example, y is x squared plus 8, right? Y is x squared plus 100, right? Y is x squared plus pi, and all of these are solutions to this differential equation, right? So the constant doesn't matter what you change it to, right? You can change it to an infinite possibility of numbers, right? Because when you take the derivative of it, it's always going to be 0, right? When we're talking about a constant. And so this is the reason why we have to distinguish between general solutions and particular solutions. So y equals x squared plus c is considered the general solution to the differential equation to y prime equals 2x, right? Whereas when you set a specific constant, that is a particular solution. So that is the difference, is whether you're going through a specific constant or whether you're keeping the constant general in a general solution. Right, so the next example that we're going to do is to find the particular solution to the differential equation y prime equals 2x passing through 2, 7. Right, so we already established that for this differential equation, right, the one we've been looking at in this video, that we know any function of the form y equals x squared plus c is a solution to y prime equals 2x. So now we just need to make sure we find a c to ensure that y equaling x squared plus c goes through 2, 7. So what we're gonna do is just literally take the solution and plug in 2, 7. So plug in 2, 7 into y equals x squared plus c and solve for c, right? Because that's what's going to make sure that we go through that point, right? So we're going to take y equals x squared plus c, right? So y becomes 7, and then x is 2. So we know that 2 squared is 4. So if we subtract 4 from both sides, we get that c is 3, right? So therefore, the particular solution passing through 2, 7 is y equals x squared plus 3, right? And if we wanted to check this, right, we could plug in x is 2, and what we should get out is y is 7, right? Y is 2 squared plus 3, so y is 4 plus 3, which is 7. So that's how you find particular solutions, is if you want to go through a specific point, and so you want to make sure your constant ensures that, and that leads us to a discussion of initial value problems, which are going to give you an initial condition, which we can treat as a coordinate point to find our constant. So the definition of an initial volume problem is a differential equation together with one or more initial values is called an initial value problem. And one key thing to know is that you need to have the number of initial values you need is the number of derivatives you have, because basically you need to know where to start each derivative. So the number of initial values must be the same as the order of differential equations, because remember, the order tells us the highest order derivative. So this is the definition for an initial value problem, right? And this makes sense why we talk about initial values, right, where the time t is 0, right, or like the initial x value, if x represents a quantity, is 0, is because, remember, differential equations are used to see how things change over time. So they're very handy. So for an example, the first one we'll do is verifying a solution, and then the next one we'll do is finding a solution, which we haven't talked about yet. So verify that the function y equals 2e to the negative 2t plus et is a solution to the initial value problem, where we're given the differential equation y prime plus 2y is 3et, and that y of 0 is 3, right? So this tells us that at time 0 we want y to be 3. So we're given y is equals to 2e to the negative 2t plus et, but we know we also need, right, not just y to plug into the diff EQ, we also need y prime. So let's find y prime, the derivative. So the derivative of this, remember we have to use the chain rule. So derivative of the outside is going to be e to the x, right? Plug the inside in and then multiply by the derivative of the inside, which is -2. So this becomes -4, right? Because -2 times 2 is 4. And then the derivative of e to the t is just e to the t. So now we plug in y and y prime into the left-hand side, and we're going to make sure that that equals the right-hand side. So y prime plus 2y, right? Y prime we got was -4e to the -2t plus e to the t, and then 2y, 2 times y was 2e to the -2t plus e to the t. Right, so then this is equals to, right, the first thing we need to do is distribute this 2. So we get -4e to the -2t plus e to the t plus 4e to the -2t plus 2et, right? And so now you see we have a -4e to the -2t and a positive one. So those cancel out. And then we have left e to the t plus 2e to the t, right? And so when we add those together, we can add them because they're like terms. We can add the coefficients. So 1 plus 2 is 3e to the t. So we have y prime plus 2y is 3e to the t, which is what we wanted the right-hand side to equal. So we know that that's, right, we verify that the function is a solution to the differential equation. And now we need to verify the initial value, which remember we said was the coordinate points 0, 3. So if we plug that into our function in our solution, y equals 2e to the -2t, right, we should get that. So we're going to plug in x is 0 and we should get out y is 3. Okay, so y is equal to 2e to the -2, 0 plus e to the 0, right? And remember -2 times 0 is just 0. And remember that anything to the 0 power is just 1. So this is 2 times 1 plus 1. So that becomes 2 plus 3. 2 plus 1 is 3. So y is 3, and that is exactly what we wanted. So that's how we verified that that solution works for the differential equation. The differential equation and for the initial value. So now let's do some actual solving a differential equation, because you might be wondering, okay, we've been verifying solutions. How would we find the solution ourselves? Well, you have a handy dandy toolbox that we've been developing all semester, and you're gonna have to take some tools out and put them to work. So we're gonna solve the initial value problem where we're given y prime equals 3e to the x plus x squared minus 4, and we're given that y of 0 should be 5. Right, so remember in the last video we talked about what is a solution to a differential equation, right? All the way back here. Remember that a solution to a differential equation is the function y equals f of x, right? So this is, well, supposed to have an unknown function, right, that satisfies the differential equation. So we have to find, right, so here our goal, right, since we want to solve the problem, is to find a function y equals f of x that satisfies the diff EQ, right, and the initial value, which means that it goes through that point, right? So it goes through the point, right, at the initial value. When x is 0, we want it to be a 5. Okay, so remember, we want to find y. Well, right, we know, so the first step will be find a general solution. So whenever you're solving an initial value problem, you first always find the general solution and keep the constant as c. And remember that the initial value problem is what's going to give you your c. So we're given y prime is 3e to the x plus x squared minus 4. So how do we find y? Well, remember that antiderivative, or the integral of y prime, should give us the function itself, right? So that's what we need to do. So to do this, take the antiderivative, right? So the integral of y prime dx, right, that's equal to, we know what y prime is 3e to the x plus x squared minus 4 dx. And you might be wondering, why the heck is it x when my variable is y? But remember, y prime is representing a function, right, which is the derivative of f of x, right, where y is f of x. So y is still just some function of x, okay, which we see here when we plug in y prime. Okay, so now we can do the derivative term by term, right? So the derivative of this, the antiderivative, remember the antiderivative of e to the x is just e to the x. Antiderivative of x squared, we use the power rule. That means we add 1 to the exponent, divide by the new exponent. And derivative of a constant, remember we add an x. And then we have our c, right? And the derivative of y prime, the antiderivative of y prime, we know is y, right? And so we can basically, we can call this C1 and C2 if we want to be really, really technical. Basically, you need to just know that you need to add a constant to one of the sides, right? But technically, both of these integrals give you a general constant, right? But when we subtract this one over from this one, right, that's just some other constant, right? So when we do that, we get y is 3e to the x plus x cubed over 3 minus 4x plus c2, and then, right, we subtract c1 from both sides. And then, right, what we're going to do is just let c be c2 minus c1, because there's no point of having this whole formula here when this is just some other constant, right? A constant minus a constant gives you another constant, right? So then y, the general solution, is just 3e to the x plus 1/3 x cubed minus 4x plus c. So this is the general solution. And now we need to find c so that it satisfies the initial value problem. So step 2 will be to plug in y of 0 is 5 to find c. Right, so our formula, y is equal to 3ex plus 1/3 x cubed minus 4x plus c. So now I'm going to plug in y is 5 and x is 0. And then we're going to solve for c. Right, so we get 5 is, remember, e to the 0, anything to the 0 power is just 1. 3 times 1 is 1. 0 to the cubed power is just 0. Right, times 1/3 is 0. And 4 times 0 is also 0. Then we have a plus c. Right, so 5 is equals to 3 plus, c. So when we subtract 3 from both sides, we're going to get c is 2. So therefore, the particular solution to the differential equation satisfying the initial value y of 0 is 5 is, right, we have our general equation, which is y equals 3e to the x plus 1/3 x cubed minus 4x plus c. But now we know we solved for c, so we can plug that in, right? So this becomes plus 2. And that is our solution to the initial value problem, right? Because it satisfies both the differential equation and the initial value. Thank you. Right, and so the key takeaway right before I go is to find a solution to a differential equation, integrate y prime, right, or any of its derivatives.